try to give you a few results, actually, and a few proofs. And you're going to see that, I mean, I'm going to state a few results, and it's going to look very simple to you, I mean, in the process, but you have to really think that it came from this beautiful representation I'm going to introduce, and these were non-trivial results before the existence of this representation. So first, let's change, so let's fix G and the temperature T. So I'm going to only look at the Ising model. So it's Q equal 2. And because I'm going to stick to G fixed and T fixed, I'm going to just drop them from the notation. So I'm going to say mu is the Ising measure. And notice that mu of sigma is 1 over a certain constant times exponential of minus 1 over t, and the sum over the pairings, like the sum over pairs with different spin, you can rewrite it in this case as just sum for x neighbors of y of sigma x, sigma y. That's another way of looking at it. Okay? And there is a plus, sorry. So this is another way of writing the measure. It's exactly the same measure as before. It just uses that my spin sigma x, because it's the Ising model, I'm going to call the colors minus and plus, and in this case, this is exactly counting the number of disagreeing neighbors. Okay? Very good. So what is my representation? I mean, how do I construct my representation? So it's going to be called the random current representation. And it's going to be very simple to define, random current representation. So what is a current? Well, a current is just a function n from the set of edges in my graph into the integers. That's all. And what I'm going to say is for an edge xy, I'm going to just write nxy for the current at xy. This is just the definition of a current. So far, it's not clear why I'm calling this a current. But you're going to understand why in a second. The second thing that I'm going to introduce is the notion of source. So a source is going to be the set of vertices, this time, of my graph, such that if you sum the currents on the edges which are incident to this vertex, so if you do the sum of nxy for y neighbor of x, you get something odd. You get either odd or even, where the set of vertices for which you get odd, you call it the set of sources. So the reason why you call these currents and these sources is the following. Let's take for a moment a current, n, which doesn't have sources. So it's only at every vertex you have an even sum. This sum is even. How can you create a current without sources? Well, there is a very easy way, which is you take a loop, not necessarily self-avoiding, take a loop, and you just look at the occupation time, the number of times you go through every vertex. This gives you a current. Okay, it gives you a function. And by definition, because it's a loop, every single time you arrive somewhere, you leave from this somewhere. So there you get no sources. So if you take a loop like that, you get a sourceless current. Now, if you take a superposition of loops, you get also a sourceless current. And in fact, the reverse is true. Any sourceless current can be obtained as a superposition of loops. And these loops in physics, you can interpret this as eddy currents. Sometimes people call it eddy currents. Now, why do we call these guys sources? Imagine now I introduce sources at 2 points. How do you construct a current with sources at these 2 points? Well, what you can do is, if you have sources, start from one point, from one of these sources, and proceed by deleting edges one by one. You know, you go through edges, and you reduce by one. You imagine you are erasing behind you. Then you will necessarily stop when you arrive at the other source. You cannot stop before, because every time you arrive somewhere, you have a way to go away because it's an even vertex. If you think about it, a source, if you have two sources x and y, then necessarily you have a path from x to y. Necessarily. So in fact, a source, a current with sources at x and y is going to be the superposition of a path from x to y and loops. And you can check that with any set of sources, in fact. It's always going to be a superposition of a certain family of paths and loops. So you really imagine you have a sink, you have a source and a sink. You start from one of the sources, you go to another one, you start from a source, you go to another one. Once you have done all of this for every sources, then you have only loops anymore. So that's the interpretation, and that's why you call it like that. So far, there is virtually no connection to the Ising model, right? So let's carry on that way. And let's introduce the following. It's going to be the weight of a configuration, of a current. It's just going to be the product over every vertex in your graph of 1 over t to the nx, every edge, on your graph, 1 over t to the nxy divided by nxy factorial. You don't know why this is a weight, why this is an interesting quantity, you are going to see in a second. So this is a definition. Now what is the connection to the Ising model? So let's introduce one last definition and we can do it. Let's call z of g, a, and t, which I'm just going to call it z of a, is going to be the sum over every configuration sigma. So I sum over every configuration e to the minus 1 over t times the Hamiltonian. And here I'm going to just put the product of the sigma x for x in A. So A is a subset of the vertices. So what is this? It's just a sum over every configuration. If you forget this term, you just sum the Hamiltonian. So what do you get? You get exactly the constant, the partition function, the constant that you saw in the first talk, which was renormalizing in such a way that you get a probability measure. So if you take A to be the empty set, it's just this renormalizing constant. But if you take A to be, say, any type of subset of V of G, then you have this additional product of the spins at A. So for instance, how do you write, so just an example of one application, how do you write the average of two spins? Well, if you think about it, it's the sum over every configuration of sigma x, sigma y times e to the minus the Hamiltonian divided by the partition function. So this is just z of xy divided by z of the empty set. With this definition, it's exactly that, right? Okay, so this is a definition. And now let's see the first theorem somehow in this area. So proposition, or theorem. Well, in fact, when I look at z of A, this is just the sum over currents n with sources exactly equal to A of W of n, of the weight W of n. And there is just a 2 to the G, 2 to the power G in front. So up to a multiplicative constant, 2 to the power G. In fact, this guy is just equal to the sum of the weighted currents. The only restriction is that the currents are exactly the currents with sources at A. Okay? So this is the first theorem. And notice that in this case, it gives you something very nice, because it tells you that mu of sigma x, sigma y, you can rewrite it as just the sum. I'm going to drop currents n. I'm just saying sum over currents with sources x and y of W of n divided by the sum over sourceless currents of W of n. Right? This directly implies this. So you can rewrite somehow, you can rewrite the spin-spin correlations in terms of sum of the weighted currents. Okay, I need to tell you how you do that, and in fact, it's very simple. So let's, do I have a second thing maybe? Oh, perfect. So let's try to prove that. So Z of A is a sum of a sigma of the product of sigma x for x in A times exponential. So exponential of minus 1 over t times the energy. This is exponential of 1 over t times this sum. I can write it as the product over x neighbors of y of e to the 1 over t sigma x sigma y. It's the same thing. But now this thing, I'm going to do the simplest thing I can think about. It's just I'm going to Taylor expand it. This I write it as sum over nxy equals 0 to infinity of 1 over sigma x sigma y over t to the nxy and 1 over nxy factorial. I just write it like that.
It's very difficult to see in the shadow.
Ah. May the light be on this. Okay. So you Taylor expand this, and now you get the sum of a product of a sum. So you remember your kindergarten, and you just say, OK, I know how to exchange the sums. And this is like the sum over n, so over any type of function n. And then what I'm going to do, I'm going to get the sum of a sigma here. So I'm going to try to put everything that doesn't depend on sigma here. So what doesn't depend on sigma? Well, the 1 over nxy factorial times 1 over t to the nxy for the product on every x and y. So here, I'm going to get the product over every x connected to y of 1 over t to the nxy over nxy factorial. I get exactly the weight. So I get w of n. And I get the sum of a sigma of, well, the product over every x in your graph of sigma x to the sum of nxy for y neighbor of x, plus, possibly, if x is one of the elements of A, I have an additional 1 coming from this product. So plus the indicator that x belongs to A. So you just do that. I mean, you just exchange. I can really, I mean, I'm certain everybody in the room can do that. So I'm not going to spend more time on it. So you exchange the two, and you get this. Now, so this is the sum over every possible configuration of a certain product. Imagine for a moment that this is odd for a certain x. Okay? Then you are summing over every configuration. You can pair a configuration sigma with the same configuration, except that x, I mean the spin at x is switched from plus to minus or from minus to plus. So by pairing like that configurations together, they are going to exactly contribute a certain value and minus this value because of the sigma x to the power odd, so just sigma x. So what I'm saying is that if one of these guys is odd, then the sum is 0. The sum of every configuration is 0. And if if for every value of x this is even, then you are just summing 1. So you get 2 to the number of vertices, because this is exactly the number of configurations. So this thing here is equal to 2 to the number of vertices if sum of the nxy plus indicator of x belongs to A is even for every x, and is 0 otherwise. But this is exactly, this even for every A is exactly saying that the sources are A, are the set A, right? If x is not in A, this gives you that this is even, and if x is in A, that means that this is odd. So it's exactly the sources. And this is the end of the proof. So it's a very simple proof. Well, first corollary, which I'm certain that if I ask you to prove it by yourself, without this thing, it's not very simple, is that I told you that the Ising model and the Potts model, they are ferromagnetic. Spins prefer to be aligned. So that means what? Concretely, that means that if I look at this average, it should be positive. Sigma x and sigma y are positively correlated. Well, it's obvious, right? With this expression, it's obvious because these are just positive terms. So you have just corollary mu of actually any product of sigma x for x in A is going to be larger or equal to 0, whatever A. And this was called the first Griffiths inequality. It was not at all a trivial inequality to get. And here, I mean, you have a proof basically in a few lines. So that's the first corollary. OK, so there is something very nice about this expression, that it looks almost like a probability. No? As a probabilist, I like probabilities. So if here, instead of having this type of sum, imagine I would have the sum of a sourceless currents satisfying some property. Then that would be very nice for me, because that would be the sum of every configuration of current satisfying something W of n divided by the sum of every sourceless current W of n. So this will scream at you that you could take a random current by saying I take a probability which is proportional, a current proportionally to W of n, and I'm looking whether my current is satisfying some property or not. So that would be perfect for me. The problem is that, you see, the sum here is not at all related to, I mean, it's not the sum on sourceless currents. There are sources there. So it's a sum on a completely different set of currents. So the next lemma is going to be somehow a way to solve this problem. And in trying to solve it, something very interesting is going to happen. So the next lemma is called the switching lemma. And the switching lemma is saying the following. So we are going to do something a little bit more complicated. We are going to sum, but on two types of currents. So I'm going to have a current with two sources, x and y. This is my current N1. And I'm going to have a second current with sources A. I'm not telling you what A is. And let's say that I'm summing, so on these pairs of currents, this quantity, W of N1, W of N2. Then, what I want to do, what the switching lemma is going to tell me, is that I'm allowed to switch the sources from there to there. The sources that are at N1, I can put them on N2. So let's write that. So it's going to be exactly the same as before. Except that now at N2, in fact, the sources are going to be, you know, if I pass the sourcing from N1 to N2, then the sources at N2 are going to be basically the symmetric difference of A and the sources at X1 and at N1. So I would like to write it like that. The problem is, imagine for a moment that the sources at A are XY as well. I'm just trying to give you an intuition of what I'm going to write. So imagine that the sources at A are also X and Y. If I write it like that, here I'm going to get sources at, empty sources. And here I'm also getting empty sources. This is a symmetric difference between the two sets. But here there is something very bad that is happening somehow, is that here you see, because you had sources at X and Y, somehow X and Y, they had to be connected by the current, in the sense that you could walk from X to Y only stepping on edges with positive current. This was necessary because I told you that a current with sources at X and Y, it's made of a path from X to Y and loops. And it's not at all the case on the right-hand side. If you take A to be XY, then you have no sources. Neither N1 nor N2 has reason to actually connect X and Y. So it looks fishy somehow. And in fact, what is beautiful in this lemma is that indeed this is a completely wrong equality, but the only thing you need to do is to add the indicator that x is connected to y in n1 plus n2, meaning exactly that you can go from x to y only stepping on edges for which the sum of the two currents is positive. This is an equality. And it's a beautiful combinatorial argument. It's a one-page proof. It's completely elementary. I do not have time to present the proof here, but it's really very simple. It's basic. I'm not hiding any demon there. It's very simple thing. So why is it useful now? Well, let's take mu of sigma x, sigma y, and let's square it. So this is just z of xy squared divided by z of the empty set squared. So you see, this is what? It's the sum of a pair of currents of Wn1, Wn2. N1 would correspond to the first sum, N2 to the second one. And the sources are exactly xy and xy. Apply the switching lemma. This thing there is becoming the sum of a sourceless current this time, W of N1, W of N2, times the indicator that x is connected in N1 plus N2 to y. And this guy is just the sum of a sourceless current of Wn1, Wn2. What did we gain? Well, we gained that now we exactly have what I was seeking for just before, in the sense that now I have the same space on the bottom and the top. So this is exactly, somehow, the probability if you take two currents, two independent currents, each one they are sampled proportionally, so it's sourceless currents, sampled proportionally to just W of N1, W of N. I take these two independent currents, I sum them, and I look whether I'm connecting x to y. So I translated the square, and not just the spin-spin correlation, the square of the spin-spin correlations in terms of geometric properties of a sum of two currents. So this is what we call a geometric representation. The spin-spin correlations are translated into connectivity properties of somehow a random subgraph of the plane. You can see of the graph. You can see this as you can look at the trace of the sum of the currents. So you just look at edges which have a positive sum of two currents, gives you a random subgraph of your graph G, and you look at the connectivity properties of these guys. Okay? Okay, so that's basically the end of what I wanted to say on the global things, generalities you can get with this random current. Now let's speak about really applications of this. So I should say, this random current representation was really Michael's baby. So, one of them. And it made, I will tell you at the end what was the original motivation. But I want to finish by that because this is really a beautiful result. So this was for the definition. Now let's try to get applications. So the first application, I already mentioned it, is this first Griffiths inequality, the fact that the product of the correlations is larger or equal to 0. By the way, notice that if A is odd, there are no currents with odd number of sources. And that's very good because the measure mu is symmetric by plus minus. So if you do the product of an odd number of spins, you get 0. On the other hand, if you have an even, then you really get something strictly positive. So in fact, it also gives you strictly positive. Second thing, I told you in the first lecture that there was this critical value. There was a value at which you start to have ordering. And below this, you do not have ordering. If you think about it, this was, sorry, the opposite, because it's in terms of temperature. This is not completely obvious. I mean, if you think about it, it could be. Indeed, the intuition is telling you the smaller the temperature, the stronger the ferromagnetic force, so the more ordering you should have. But this is just at the level of intuition. Why is it that, in fact, when you decrease the temperature, basically the correlations increase? Well, I can prove that. So, so this is application, sorry. So this is going to be one application, which is, let's differentiate with respect to 1 over t, mu of sigma x, sigma y, the spin-spin correlation at 2 vertices. Well, it's a very simple exercise. Once again, kindergarten type mathematics, to say that it's the sum of a neighbors of b, or let's say z neighbor of t, of mu of sigma x, sigma y, sigma z, sigma t, minus mu of sigma x, sigma y, mu of sigma z, sigma t. Just to differentiate the thing in 1 over t, it's immediately what you get just from the definition of the measure. It's very, very simple computation. So this is going to be positive if this is positive. Right? So this is what? Well, it's z of x, y, z, t, z of empty set, minus z of x, y, z of zt, divided by z of the empty set squared, right, with the definition of our partition function. So here you have a sum. Here you can see it as a sum over n1 and n2, n1 at sources at x, y, z, t, n2 has no sources, and here is a sum with sources at x and y and sources at z and t for n2. Do the switching lemma once again. Here, switch the sources of zt of n2 to n1. Then you get exactly a sum where the sources of n1 are x, y, z, t. The sources of n2 are none. There are no sources. The only thing is that you have an additional constraint, which is that z has to be connected to t. So you are summing over every current like that, and you are subtracting currents like that satisfy, in addition, that z has to be connected to t. So this big thing is positive, automatically. If you try to prove that, it's the second Griffiths inequality. It's not trivial at all. And here it's very simple. Of course, it's not very difficult. I'm not saying that proving that this is increasing is difficult, but it's definitely harder than like that. Okay, this is another thing. Now let's go into a little bit more difficult application, and then I'm going to be a little bit less able to explain the proofs because I don't have time. But there is one application, for instance, is that when you have a critical temperature, you expect that above this critical temperature, you know that the spin-spin correlations that tend to 0. This is basically the definition of the critical temperature. But in fact, you expect them to decay exponentially fast to 0 with the distance between x and y. And this was a result obtained by Eisenman, Barsky, and Fernandez, which was proving that indeed, for every t larger than Tc, there exists a constant c, which depends only on t, such that if you look at mu of sigma x, sigma y, it's smaller or equal to e to the minus c x minus y. So it's called a sharp phase transition. As soon as you are above the critical temperature, you have exponential decay of correlations. And in fact, the result was even nicer than that because it was also saying that below the critical temperature, when you look at the magnetization, the spontaneous magnetization that I defined in the previous talk, this kind of defect on the symmetry breaking, the density of the pluses compared to the density of the minuses, they also proved that this was larger than a constant times square root Tc minus t. And this square root is actually related to the fact that here it's the square, which is expressed in terms of correlation of the random current. So this was a proof from the 80s. I should mention that there is a new proof by Vincent Tassion and myself, which has, I mean, both is like, I mean, only a few pages long, but which uses a fairly different approach, but is also based on this random current representation. So both proofs of these things, they use a random current representation. We don't know any other proof of this general fact. Good. Let me tell you another application of this is exactly what I was mentioning, that the magnetization, I mean, the phase transition is continuous in dimensions 3 and more. So the magnetization at Tc in dimension d is always equal to 0 for any d larger or equal to 2. So you always have a continuous phase transition, and in particular, in dimension 3, the phase transition is continuous. So this was a result by Eisenman, myself, and Sidoravicius. So to this point, I mean, just as the first Griffith inequality is a very old result, it goes back to the 60s. This is also, I mean, is even older. This is a result from the 80s, early 80s, and this is a result for 2013, something like that. So what is the big difference? I mean, why did it last so long in between? That's a good question. And the reason, maybe just in a few words, is that this expression in terms of, this interpretation in terms of subgraph of, I mean, random subgraph of the plane, geometric properties of random subgraph of the plane, was not really the way people were looking at the random current representation before. They were rather using the random current representation and this switching lemma to derive differential inequalities on thermodynamical quantities. So that's exactly what is used in this Eisenman-Barsky-Fernandez result. But somehow here, the new inputs, I mean, coming from probability and from, you know, all this theory of percolation and so on, I mean, just when I look at this model, for me, I just want to study the geometric properties of this random representation. And what happens is that in dimension 3 and more, what you can prove is that when you look at this sum of two independent currents in the full plane, you can actually prove that there is no infinite cluster at criticality. There is no infinite connected component of edges for which the sum of the two currents is positive. And if you prove that, you prove continuity of the phase transition. So some people, I mean, just maybe some parentheses of 5 minutes, then I will go back to proving things, but just for people who know a little bit more about that. So you have this percolation type model. You look at this random subgraph of the plane of ZD, and you prove that at criticality there is no infinite cluster. I mean, if you think about it, that's a very strange thing that you are even able to do that. Because there is another classical model of probability, which is called Bernoulli percolation, for which every edge of, I mean, you obtain your subgraph by just saying every edge in your graph is in your subgraph with probability p, is not with probability 1 minus p, and this independently of all the other edges. So you choose independently for every edge whether it's in your subgraph or not. So this seems like the simplest definition of a random subgraph of ZD you could imagine. And for this model, there is also a phase transition. There is also a critical parameter p at which you start to have an infinite cluster. And it's a widely open question to prove that at criticality you do not have an infinite cluster. It's a big question in probability. Beautiful question. And it's very strange that it's difficult, but it is difficult, trust me. We are sufficiently many to have tried. It's a difficult question. So here, why do we, I mean, this model seems even worse, you know, I mean, the state of edges is really not independent at all. Here, it's a nightmare to actually understand the geometry of this guy. So what saves us here? What is the difference? Well, the difference is that for the Ising model, you have a beautiful Gaussian bound, which is called the infrared bound, which allows you to bound the spin-spin correlations by the by the correlation of the free field. So this bound, you cannot directly use it at criticality because, in fact, it doesn't really give you a bound on the spin-spin correlation, but on the truncated spin-spin correlation. So you cannot use it directly to prove continuity. But somehow you can still use it just below PC, then let P, just below TC, sorry, or just above TC in the disordered phase, and use this information to actually prove that indeed for this sum of two currents at TC, there is no infinite cluster. So of course, there is an interchange of limits which is not at all trivial to make. That's exactly the content of the theorem. But I just wanted to tell you that really the trick, the thing that you do not have for percolation, which is actually wrong for percolation, is this infrared bound that you get from this. And that's how you get this magnetization. If people are interested after the talk, I can explain more how you prove this. So this was maybe in the context of the first talk, basically the end of this one, in the sense this is the answer in higher dimension. It's always continuous for dimension 2, for Q equal 2, for the Ising model. So in some sense, this big conjecture about the order of phase transition for Potts model, you always, for all the continuous values, you know, all the values for which it's expected to be continuous, you know that it's continuous. For the discontinuous part, it's a little bit trickier, but like that, I still have some work to do. Okay, let me finish by a new observation that we made in the spring with Michael when I was visiting Princeton, which I think is absolutely beautiful, and we don't know yet how far we are going to go with that, so it's more, ongoing project than anything, but it really hints towards something beautiful. So there is a quantity in field theory which is very, very useful, which is called the Herschel 4-point function. So it's just, the idea is that you want to take well, let's now say sigma 1, 2, 3, and 4. So you want to take the 4-point function and you want to truncate it. If you would have a Gaussian process, if you want to truncate it, you truncate it by the Wick product, what we call. So meaning you subtract all the possible pairings. So you do sigma 1, sigma 2 times sigma 3, sigma 4, minus mu of sigma 1, sigma 3, mu of sigma 2, sigma 4, and minus mu of sigma 1, sigma 4, mu of sigma 2, sigma 3. And this is really a quantity you want to understand as a field theorist. And the beautiful thing with the random current is that you can guess that you can probably get an expression for that. In the following sense, if you rewrite this once again with these sums like that, you are going to see that this is basically z of 1, 2, 3, 4 times z of the empty set, minus z of 1, 2, z of 3, 4, minus z of 1, 3, z of 2, 4, etc. Switch the sources of 3 and 4 to 1 and 2, the sources of 2 and 4 to 1 and 3, and the sources of 2 and 3 to 1 and 4. You always get a sum where the current N1 has sources 1, 2, 3, 4, and the current N2 has no sources. It's just that you have different constraints. Here you have the constraint that 3 needs to be connected to 4, here 2 connected to 4, and here 2 connected to 3. When you massage this, it's it's 3 lines. What you get is that this thing is equal to the following. Is equal to mu of sigma 1, sigma 3, mu of sigma 2, sigma 4. There is a minus 2 in front. And here, what you get is you are going to get exactly the sum over N1 with sources 1, 3, and N2 with sources 2, 4. So the sum of Wn1, Wn2. And at the top, you are going to get the same sum, except that you are going to have an indicator that 1, 2, 3, and 4 are all connected together. So you have to trust me. You can really do it yourself. It's really 2 lines. You can check it's an identity. You have something like that. OK, very well. It doesn't seem to be so impressive, right? But look at the following observation. Take planar lattice. Take a graph, a planar graph. and take 1, 2, 3, and 4 on the boundary. You take 1, 2, 3, and 4. So what I'm saying is you are looking at the spin-spin correlation on boundary vertices for a planar graph. Here, you are summing over sources at 1, 3, over a current with sources at 1, 3. So if there is sources at 1 and 3, necessarily in N1, 1 is connected to 3. That's necessary. You are taking sources for N2 and at 2 and 4. So 2 and 4 needs to be connected necessarily. What do I get? I get that, in fact, 1, 2, 3, 4 are automatically connected to each other. So this quantity here, in this context, it's equal to 1. But look, this is exactly what you recover here. So the 4-point function in this case, you can write it as the product of these two things minus the product of these two plus the product of these two. It's called a fermionic-Wick rule. It's like the Wick rule, except that you have, in fact, the signature of your pairing. And this is a very well-known fact about the two-dimensional Ising model coming from this Onsager solution. Actually, it goes back to this, but there are new ways of seeing it, that indeed the 4-point function, and you can do this for the 2 endpoint function, satisfies what we call a fermionic-Wick rule. But the whole point is that, as it was proved before, it was really using the fact that, in fact, the partition function for the Ising model in 2D can be written in terms of Grassmann variables. It can be written as a Grassmann integral. And this was very much related to exact planarity. It was very much related to the exact solution of the Ising model. But here there is something more interesting happening. Is that imagine your graph is not really planar. Imagine it's two slabs, one on each other. Or imagine, for instance, instead of being nearest neighbor, allow pairing between next to nearest neighbors. Then the graph is not planar anymore. So then this probability is not 1. Maybe this guy can jump above the other one. So they do not necessarily intersect. But these guys, at criticality, these currents, you should really think of them as fractal objects. And if they pass above each other, they are going to pass above each other in many places, and they have no real reason not to intersect. So in fact, every place where they pass above each other, they have positive probability of intersecting. So what I'm saying is that at criticality, even for this not really planar guys, but almost planar models, in fact, these things should tend to 1 when you take larger and larger graph. So you should get an asymptotic fermionic-Wick rule. And this is something from the point of view of universality. There is something beautiful happening here. That, the Ising model, there is this big belief in mathematics that, in statistical physics, that all these models, they should be universal. If you define them a little bit differently locally, for instance, if you use these next to nearest connections, couplings, you should basically get the same exponents, get the same behavior, and so on. But this is very far from being understood mathematically. But maybe this is actually a good direction, because here the only thing I'm using is the gauge theory plus minus of the things, just the symmetry, which allows me to give myself this nice random current representation, and the planarity or the quasi-planarity of the graph. So I'm using the smallest amount of information I can hope on the Ising model, and I recover this asymptotic Wick rule. And this asymptotic Wick rule, by the way, just for information, it gives you the exponent on the boundary. And you can extend this even to order-disorder operators in the bulk and so on. So you have, it's not restricted to this boundary correlation. So here there is something very interesting from the point of view of universality, I think, which deserves to be understood. Let me finish these two talks by the beginning somehow. Why did Michael Eisenman introduce this random current representation? Take the model in dimension 4 and more. There, if you take 4 points, the two currents, they have no reason to intersect. The two, I mean, there is a path from 1 to 3, a path from 2 to 4. You are in dimension 4, there is a lot of room. There is no actual reason they intersect. And in fact, you can check that these guys, they behave roughly like random walks. And indeed, in dimension 4 and more, these random walks, they do not intersect. So in fact, Michael Eisenman was able to use this intuition to prove that this term tends to 0 in dimension 5 and more, and even in dimension 4, we tried to prove it, but it should also be true in dimension 4. But in dimension 5, it is actually proved. So that means that the 4-point function is asymptotically equal to the Vig product of the pairings. And this is exactly saying that the asymptotic, I mean, the quantum field series that the field series that you will get from the just scaling limit of the Ising model is trivial, which was bad news somehow, because I mean, there was a beautiful hope, because this was a very natural thing to expect, that in order to construct a non-trivial field theory in dimension 4, you could use the Ising model or the 5-4 model, which is a model for which you have the same type of things, to actually construct something non-trivial. And this result tells you, well, it's actually trivial. This field theory is trivial. So you cannot use this thing. You need to do more work there. So this was the original motivation for Michael to introduce this thing, and I think I'm going to finish on this nice result. Thank you very much. It is trivial, but we don't know how to prove it. That's really something which is important to recall, because I think there was some confusion at some point. I mean, the exponents, the critical exponents are known. This, you know that they are the mean field exponents. But the triviality really of the field, so the fact that this thing is tending to 0, we do not know how to prove. At least Michael and I don't know how to prove. And we are trying, and it's doesn't seem so far, but still it's kind of resisting for, I mean, going into the geometry of these random currents at criticality is actually very tricky. It's really something difficult to do. Probably at some point we will manage to understand something that will really unlock everything, but today it's difficult. So we don't know that. Yeah.
Also, there's a similar work of Fröhlich.
Exactly. So Fröhlich has a, so this, I mean, maybe to complete this, so I didn't mention it because it's a different type of geometric representation somehow. So I like this representation because they are representation in terms of random subgraphs. So there are a whole class of beautiful representations which are based on random walk type representations. And indeed, there is a representation by Jörg, who is actually also allowing to derive the same type of things. And in particular, the triviality in dimension 5 and more is you can prove it using this representation. But this, sorry?
This representation was introduced by Kurt Szymanczyk.
Sorry? The random walk, you mean? Yes. I mean, so Szymanczyk was, I mean, actually, I think he introduced even in a larger context, right? I mean, that's how to expand in general all this Hamiltonian instead of yeah. So basically, you see, you want to compare to random walk. In higher dimensions, the infrared band really allows you to do crude bands somehow, and it's sufficiently strong. In 4 dimensions, the bounds that you get from the infrared band are just failing by a little bit, just by a little bit. So what you need to prove is really to go a little bit farther, like the next step in comparing to the random walk. And my intuition, like, I mean, what I see that we are missing and that you need to prove is you need to prove some kind of mixing for this path. You need to prove that, you know, if I tell you what it's doing locally, then very far away, the path doesn't remember what it's doing locally. It's certain this is true, there is no doubt about it, but proving it is difficult. And you need the same thing if you look at this path in the random current representation, or if you look at the random walk representation, same thing, this random walk representation, you need to prove that the random walk is mixing, basically. That's the same difficulty, I would say. Yes?
So some
Yes.
So, is there any random walk intuition corresponding to the continuity of the phase transition?
So, sorry, in dimension 3 and 2, well, in some sense, these random walks in dimension 2 and 3, you can also, I mean, these are random walks that just they do not behave like the simple random walk. They are going to behave like random walk in random environments, basically, because there are these loops that they are, which are a little bit repulsive for these walks. So they are going to have a different geometry, which is going to be related to the critical exponents and so on. But it's exactly, I mean, what I'm saying is difficult to look to, I mean, in the geometry of these guys, it's exactly that, because then they really interact with their environments, which is not the case in higher dimension. And in particular, in 3D, you do not expect it to be trivial. That's one of the points.
And the field theory exists.
Sorry?
The field theory exists.
Yeah. But the connection to the discretizing model is not known rigorously. Sorry? Thank you.